All right, basically time to get started already. I want to make people aware of something that I added to Canvas yesterday that will be useful throughout the entire quarter. And it's an application that was actually made by the students of the authors of the textbook that I pulled a lot of this from. It's called JFlap. So it's in everything that is added to this course is going to be in the modules of the Canvas. So that's where all of the slides will live. That's where just all of the resources for the class will be. And that includes a link to the JFlap site. Everything that we cover in this class is theoretical, but it's also very diagram heavy, and drawing out diagrams can be really annoying, and JFlap helps you to be able to have a playground to play around with everything that we're going to be covering. So I highly recommend you check out the tool, get the tool, and that way you can also make the diagrams using that tool for assignments. I'm not going to require you to do that. If you want to draw it out as you're problem solving it and then take pictures, that is absolutely fine. But I've had students in the past also tell me that JFlap was way easier for them to use. So I highly recommend just playing around with it as we start to cover the material where you'll be able to engage with it. And by the end of today's class, we'll at least have, I believe, introduced our first automata type. So you can start to play around with it, making those kinds of automata. And as we continue to explore new topics, all of those are supported by this tool as well. So I think that will help a lot. Any questions before we get started? Reviewing and continuing on with new stuff? All right, last time we were talking about grammars, and I wanted to draw out something that I've been using in office hours and just throughout other conversations with people to try to help this process make a little bit more sense, because I think it'll help this to make a little bit more sense. So recall that a grammar is a quadruple or a four-tuple or a tuple of four elements, whatever you want to call that. We had the non-terminals, we have the terminals, we have our starting non-terminal, and we have our sequence of productions, our set of productions that is defined to just be every rule that we could apply as we go from this start non-terminal to be able to produce any string that would be in a language. So let's take a look at what happens if we start with kind of I'm going to draw this out like a tree. We start with the start non-terminal. I'm just going to, how do I do this? I'll draw it here. We're going to use, this represents just that we have the start non-terminal. We need to parse the start non-terminal and produce something from this. So whenever we go to, this is going to be a binary tree. Whenever we go to the left child, we're going to be applying this rule. Whenever we go to the right child, we're going to apply that rule. So what happens if we go from the start non-terminal and go to the right child? This start non-terminal is replaced with the empty string. So we get the empty string. And we'll note that whenever we go down this right child, we are terminating and creating a sentence in this language. Whenever we go down the left child, there's still going to be, we're recursing, but we're also still having this non-terminal or this variable that needs to be evaluated before we continue that process. So if we go to this left child, this node is going to have the value, and maybe I just want to draw this out. Instead of nodes, I'm actually just going to draw the string. So we would just have ASB at this point as this S turned into an ASB, which is what this rule is telling us. Replace the left-hand side with the right-hand side. This A and B are terminals, and the S is a non-terminal. From here, we can split into a left child and a right child. If we go to the right child, we're turning this S into an empty string, so we generate just AB, a sentence in the language. Because we were able to start with the start non-terminal, apply production number one, followed by production number two. Production number one goes the left child, production number two, the right child. Since we could generate this from this grammar, this is a sentence in that language. If we apply the first production from ASB, we're going to carry down this A and this B. And what goes in the middle here is the application of turning this S into ASB. I actually should give myself a little bit more room here, probably. So we have the A and the B from here, but this S turns into that ASB. From here, this can become a left child or a right child. If we apply production number 2, then this S becomes the empty string, and we get AABB. If we apply left child, we apply production number 1. This becomes, we bring down the A and the A, we bring down the B and the B. This S becomes ASB. And you can see how this process continues infinitely. So this would be AAA, BBB, and this would continue to produce more and more of those. So this tree is infinite. This language is infinite. But now we can start to see how this represents the language A to the N, B to the N, which just means N A's followed by N B's. If we just go to the right child, it's A to the 0, B to the 0. If we go here, it's A to the 1, B to the 1. Here, A to the 2, B to the 2. And if you wanted to come up with an algorithm for this, it'd be the number of left child, number of times we went to the left child, followed by a guaranteed right child. The number of left children we went down is the N that would be represented in A to the N, B to the N. You go left, right, you get A to the 1, B to the 1. Left, left, right, A to the 2, B to the 2. Left, 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 right, A to the 3, B to the 3.
Could you just repeat that rule one more time? You said if there's, for every left child, there's a right child, and that's an N.
So it's the number of left children we go down. This is just for this grammar. This will not apply in general, but I want to go from this really theoretical concept to being able to draw it out, hopefully in a way that you can visualize and understand, and give a little bit more pattern to it, so that those of us who are pattern recognizers can start to see, 1, this is infinite, and 2, there are still strings in the star closure of this alphabet that are not anywhere in this tree. So no matter where we go, we never find BA. That is never anywhere in this infinite tree. Question?
Could you change it so that there's some sort of limit for N? So that we go to infinite?
Yes, we will actually talk about the kinds of languages that we can produce. Those different languages that will fall into one of the many language types that we discuss. And we're going to start having restrictions both on grammars, and when I introduce state machines and drawing out state machines, we'll be able to see what kinds of languages are in one or another. But absolutely, you could have a language that says A to the N, B to the N for all N less than or equal to some arbitrary number. Absolutely. That would be a finite language.
Because there's no production to get, this is an incomplete grammar, right? Because you can't get BA.
It's complete in that everything that is in the language A to the N, B to the N can be generated by this. And anything that is not in the language A to the N, B to the N cannot be generated by this grammar. So it's complete for that language. So I think that's how we're going to use the definition of complete. For a particular language, 2 things need to be true. Every string, every sentence that's in that language needs to be able to be produced via some finite number of sequences of production applications. Everything that's not in the language should not be able to be produced by that. So BA should not be able to be produced by any sequence of these productions, which we see when we draw it out like a tree. Nowhere in this tree will we ever generate BA, even though this tree is infinite.
And BA is not
in the language A to the N, B to the N.
Okay, so
Yeah. Other questions? All really good questions so far. So hopefully that helps us make a little bit more sense. Just so I get a sense of that, show of thumbs, how do grammars, how this particular grammar feel? Excellent, much better than we were. That's what I like to see. Also, I should note that I did upload the first couple of recordings. Since this room had sound issues yesterday, I don't know if the first recording had sound issues or not. I tested it today and this should be picking up my voice now. It looks like it is. So if that was an issue for the first couple of classes, it should stop being an issue now. But if you ever want to review any of this and watch it back, generate questions, maybe when you have a study guide and you're reviewing for an exam, those lecture recordings are there. The link is in Canvas under those modules. Okay, let's move on to an exercise. Now we're going to go the other way. I'm going to give you a language, and your task is now to come up with an associated grammar that for any sentence in this language is going to be possible via some sequence of those productions. Anything not in this language will not be able to be produced by any sequence of those productions. So it's very similar to A to the N, B to the N. It's just that there is one more B than there were A's. All A's still come before all of the B's. So maybe let's start with, what are some sentences in this language? Yeah. B by itself. Sure. What else? ABB. ABB. What else? AA. BBB. This pattern will continue. So this is n equals 0. This is n equals 1. This is n equals 2. Start with the grammar that we had on the last slide. See if you can modify that grammar to produce something. Don't start completely from scratch. Start with the two production rule grammar from there. You want to write it down. We had the start non-terminal arrow, A capital SV, or lambda to be able to terminate something. So how would we turn this into a grammar that recognizes one more B than A doing that? Question or answer?
I would answer.
Let's give people just a little bit of time to work on it. That's awesome that you have something. That way so you can see this much better. General class note, whenever I give you an exercise or something of the sort, unless I specify, you are welcome to work with people around you. You're welcome to talk it through. So get to know the people around you if you don't already from some prior class. It will be very useful in this class. I will be very frequently giving you some kind of problem and then shutting up and letting you work through it and figure it out. And a lot of times putting your heads together for something like this can be very useful for working through it, getting an understanding. Question?
Like go over what a production is again.
Yeah, that's just one of these, we have for the moment, we have a non-terminal arrow, some number of terminals and non-terminals that's going to be able to produce something. We're basically replacing this with something. So we're coming up with a sequence of productions, some number of these productions that when mapped produce that language. So if we were doing,
If you get rid of that one, then there's nothing happening. What you add, the sentences are language.
if we have this, we know this produces the language A to the N, B to the N. So what change would need to be made to these two productions to produce A to the N, B to the N plus one?
Oh, okay, so I'm ready.
What did we come up with? One person with an answer, anyone else with an answer? A few people? Yeah, what do we get? What do we change?
I kept everything the same except I added another variable A
Okay,
and then, one more production. Or I changed to the production.
okay,
Um,
what do we have?
The first production is S derives A, B, where that A is a capital A, it's a variable. So like this.
Yeah,
And then that new variable A derives a variable A, B. So lowercase a, uppercase a, and then B.
mhm,
And then A can also derive lambda.
this will work. So we can draw out an example of this. Did anyone come up with a different answer? This is perfectly valid, but I was thinking of something else. Yeah. Yeah,
I just changed S equals the S points to lambda, I changed it to B. and then
Yep.
I just had that.
that's what I was thinking of. Both of these will work.
Because it's terminal.
Let's take a look at both of these and see why they might be equivalent. As is true with just about everything in computer science, you can write the same algorithm with different code. Maybe there's an efficiency difference, but it still does, it transforms the same inputs to the same outputs for all possible inputs. So let's take a look at both of these. So because this is what we started with, I'm going to start here, but I'm also going to talk about this because I think it's important. So now if we're drawing a tree for this, this would be the left child still, and this would be the right child. But now instead of a right child just replacing that S with nothing, it's going to replace it with a B where that is. So we're still recursing in the middle of this string, but when we're done, we have to put an extra B there. So it would look like S becomes, if we're applying the second rule here, this becomes a B. So we get the B that represents that case. This becomes ASB. If we continue this process and replace this with a B, we get ABB, which is that case. We continue this process, this ASB, we bring down the A and the B, we get another ASB in here. We can turn this into AABBB by applying the second rule, or we can continue this process forever. So it's very similar to the tree that we drew for the last one. If we wanted to do something like this and show that it's equivalent, now we really have, whenever we have an S, we only have one rule that we can apply. So we would start with an S as the root of our tree, but now there aren't three options, there's only one, because there's only one rule that replaces an S. So we're going to make a single line down, and this is going to become capital AB. Replacing this A, we now have two possibilities, so this is going to start branching. But note that if we take the right child, I'm going to call this now the left child and this the right child. If we take the right child, we get rid of the A. So this becomes B, that is again, this first n equals 0 case. If we apply here, we're applying this rule. So we're going to bring down the B and turn the A into A capital AB. Since the only variable in here now is an A, there are two possibilities for this. We could split this into a left child and a right child. The right child case is a little bit easier. The H is gonna go away. We get A, B, B, which is this case. Replacing this A, we get the A, B, B that we bring down, and we get A, capital A, B here. And we just continue this process on forever. But we can see that these two trees generate the exact same set of strings. The process by which they do that is ever so slightly different, but they would be equivalent to each other. Questions on that? Yeah,
So the productions only end when there's no more option, when you're like, no more productions to apply.
yeah, so that would be kind of the leaves of this tree would be the strings or the sentences in that language that are generated. As long as there's a variable in there, there's still something abstract that we need to evaluate or resolve in order to be able to come up with some kind of sentence in the grammar. Good question. Anything else before we move on? Everyone have what they need? The rest of this slide will just do what we've already done. There's one solution. There's another one. I wanted to introduce this concept of the vertical bar because otherwise this A leads to A capital A B, A arrow lambda. Those become separate productions and separate lines. You can just, if it's the same left-hand side, you can just put a logical or there that says we can apply multiple different rules there that'll shorthand this and make it a lot easier to write. So now that you're aware of it, you can use it. Two grammars, like the solution and the alternative solution, generate the same language. If they generate the same language, then they are an equivalent grammar. We'll dive into grammars in a lot deeper level eventually, once we can restrict it a bit. But I want to introduce the concept of an automata before I do that. So an automaton, singular, is a way that we can abstract away a digital computer and actually start to write programs on paper. And not just programs in a particular programming language, but abstract logic. It's very useful and actually really cool. The entirety of this course is going to be planned as a problem-solving course, so I will always be throwing problems at you to try to make these learning outcomes happen, rather than just showing you how it works. I'll show it to you and then have 2 to 4 examples of it at increasing difficulty to make different outcomes so that you can get a chance to practice it. So I think that's really necessary. What does an automaton do? Just like an algorithm, it takes input, it produces output. The input that it takes is a string. This string is going to come with the question, is this string in an associated language? The automaton is constructed just like a grammar to represent a particular language. That string is going to get parsed character by character. And you can think of an automaton like a state machine. We're going to be in a particular state, and based on the character that we read, we're going to be transitioning between states. We just have to define a starting state and a set of final states. If we end reading this string in a final state, that means that the string was in the language. It was a sentence of that language. If we terminate in any state that is not a final state, then it is not in the string is not in the language defined by this automaton. But of course, automata can do a little bit more than that. They can not just be acceptors, they can also be what we call transducers. they can produce output as well. So they can actually write output as something like, you could write an automaton that calculates binary arithmetic, or at least binary addition. And that way the end result of this would be a binary number. So it has components, the way to read input from a string, a way to produce output to some temporary storage device, something that either says yes or no, or produces some kind of output. It also needs some kind of control unit, which is the equivalent of a computer's CPU. It's going to have some number of states, some number of transitions, and that's going to be the definition of an automaton. It would look something like this. There's an input that is just a sequence of characters that's fed into the control unit, the states and transitions. As we go through those states and transitions, reading that input, eventually we are interacting with some kind of storage. We're either moving along the storage, writing things to that storage, something of the sort. The automata that we will focus on initially does not have any of this. It's just, the output from this is just yes or no. Yeah.
It's allowed to read from its storage, right? Like it's not only allowed to read from the input file.
Yeah, so for a more complicated automata, then yes, it may be writing to and reading from the associated storage. So the automata number 1 that we will look at does not have any storage. Automata type number 2, this storage is restricted to be a stack. It must be a stack. Automata number 3, this is an infinite 2-dimensional tape. But for now, the storage won't exist. But in general, they're allowed to have storage. How that storage is restricted is up to the class of language that we're trying to accept. There are discrete time steps to this. So at any particular time, we are in a particular state. You can think of this kind of like using a debugger for code. Whenever you're reading a particular instruction or another instruction, if you were to open up the debugger and look at the associated state of your application, all of your data structures would have particular values. Every element of that structure would have a particular value in it. Taking a snapshot of your program with a particular input at a particular step, you would have a snapshot of that program. You'd be able to see the state of that program, if that makes sense. So it's very similar like this. They're going to be discrete time steps, which is why discrete is such an important study in computer science. So at any given time step, there is a state that the control unit is in. The input is reading a particular character in that input string. And the next time step is 100% deterministic and determined by the character that it's reading and the state that it's in. So we know the next state that it's going to transition to based on those 2 pieces of information. The state that it's currently in, the character that we're reading. Again, this is just a broad overview. We'll be talking about a particular type of it in a lot more detail here momentarily. As we're transitioning from one to the other, one state to the other, there may be some output that is produced or something in the internal storage is changed. So as we transition, we update the state of both the output and the storage. In general, all of this can be summarized by the term configuration. So if you were to take a tuple of the state the control unit is in, the string, as well as the character that we're currently on and reading in that string, the storage that we are using, what's the state of the storage, all of that combined is a configuration. Kind of just like the debugger, it's a snapshot in time of this automaton. We can also define a move to just be a transition from one configuration to another. What happens as we move from time t to time t plus 1? So many types of automata based on what they can do, the kinds of languages they can represent, but we're going to mainly study 3 different classes of them. And within those classes, there are going to be deterministic types and non-deterministic types. And we will talk about non-determinism probably later this week, because it's an incredibly important concept in this class and in general in computer science theory. So I will describe them here. Deterministic, we can determine the transition uniquely based on the current configuration. The current configuration will tell you exactly what the next configuration is going to be because we know what symbol we're going to read. So we can determine what transition we are going to take. If it's non-deterministic, we do not have that guarantee. There may be multiple possible next configurations. And so we need to determine, is it possible that we can have a sequence of configurations that lead to acceptance? We also can talk about the difference between an acceptor, which I talked about as it answers yes or no to whether a string is a sentence in a language or not, or a transducer that actually produces output. For this class, we will 100% be focusing on acceptors over transducers, but it's important to note that this can absolutely be done to produce output. But for the most part, we are going to be concerned about answering yes or no as to whether a particular string is a sentence in a language. Questions so far? Last thing really to talk about before we dive into something more concrete is what can we do with these? Why would we care to study them? Where are they actually used? If you are analyzing a programming language or writing your own programming language, then it's very important for syntax diagrams. If you ever needed to produce a grammar for a particular programming language, or if you were writing your own programming language, then you would want to be able to produce a grammar for that to determine whether a program is well formed or not. Compilers need to be able to do this because the goal of a compiler is to take as input a program and to say yes or no, is it in this language? So a compiler is really just an acceptor, a very complicated acceptor. It does a lot more than that usually. There's going to be some speed ups. It will determine if I can execute your program faster, consolidate your code into instructions that take less time. So compilers can be optimizers as well, but in general, the whole purpose of a compiler is really just to be an acceptor. It can also reason about the correctness of a program. So if you could take your program and represent it as an automata, then you could determine, theoretically, does this program do what I think it does or not? You convert it into a state machine. You can reason about the state machine rather than looking at and thinking about, is this Java correct? Is this C correct? Just like you can compile, I mean, a compiler basically does this already, but it converts one language into another. So you could write a Java to C converter, and that would require you to be able to parse the Java, come up with the associated C, and then output that C. Then I just wanted to give people, I've already done this, but an example of a transducer, something like a binary adder. Everything before this is usually an acceptor, except I guess the converting one language into another is also a transducer. All right, slide deck number 2 complete. Go grab slide deck number 3. We're going to start talking about our first acceptor type, the deterministic finite acceptor. Don't hate me too much for this first slide. We're going to make this make way more sense. Lots of theory on here, but we're using a quintuple to define a DFA, just like we used a quadruple to explain a grammar. There are 5 elements of a DFA. For now, don't feel like you need to memorize this or know it extremely well. We'll come back to it after we've looked at it. But the components of a DFA can be broken down into 5 categories. We have internal states. We have the alphabet that we are using. We have the transition function, which is a function that defines, given that we are in a particular state and we read a particular symbol, what is the next state? That is defined for every state character pair. And that's what this Q cross epsilon arrow Q is. For every internal state, for every character in the alphabet, there's going to be a next state that happens if we're in this state and read this character, this is the next state. But that's defined for every state, for every character. We then need a single initial state that tells us when we begin reading this input string, what is the first state that we start at? That's one of the internal states, but we only get one of those. And then we have a set of final states that says if we complete reading the input string in one of these final states, that is where we can say, yes, this string is in this language because we finished in one of these final states. If we do not complete this process in a final state, then we reject, saying that this string is not a sentence in the language. I expect this does not make 100% sense yet. Let's actually draw this out visually so that we can see it work. And then we'll come back to this to be able to say what it is. Give you a couple more seconds to write things down. Remember that these slides are also being published on Canvas. So if you're copying things character for character on a slide, I tend to find that you will have access to all of these later. It's just a matter of what is intuitive or useful to you. So what is a DFA and how does it work? All right. We're going to define this initial state. We're going to call it Q sub 0. Because capital Q was that set of states, a lowercase q is going to define a particular state. Q sub 0 tells us that is the initial state. But in general, we actually want to draw an arrow to this state that signifies that it's the starting state. And that doesn't force you to use this language to define a state. It is whatever the arrow points at that is the initial state. We start at the leftmost symbol on the input string, and we're going to be reading it character by character and making those transitions. For each transition that we take, we're going to be moving one character past into the input string. So if we have an input string that is 3 characters long, there will be a total of 3 transitions within this automaton. We're going to call the transition function here delta in a way that it's going to look like we said the capital Q cross epsilon arrow capital Q. We're going to summarize all of that as delta, the transition function for everything. So we can say the transition function from state QA when we read an A is that we end up in state Q1. So that's how we're going to read this in English. If the DFA is in state Q0, reads an A in the input, it transitions to state Q1. And we'll use transition graphs to do this. So every internal state is going to be a node in this graph, and every transition governed by the transition function is going to be an edge between those vertices. Let's give you an example so you can see how this works. Let's actually do the whole slide. There we go. All right, so this arrow tells us it's pointing at the initial state. So we're going to start here. The input alphabet for this is binary, zeros and ones. So we start in Q0. We can see that this is a final state, and we can denote this with, instead of just having a single circle, there is an inner circle to this as well. If you have a double circle, then that means this is a final state. So this edge says that if we are in Q0 and we read a 0, we transition from Q0 to Q0. On the other hand, if we're in Q0 and we read a 1 in the input string, we're going to transition from Q0 to Q1. So if the input string were something like 0, 1, 1, starting at Q0, because that's where we start, because this is the arrow that points at that, you always start here. We're going to read the 0. This says we're going to loop to Q0. We've then read that, so we're done with it. We move on to this 1. We're going to transition from Q0 to Q1 as we read that 1. Now we're in Q1. When we read this 1, we're going to transition from Q1 to Q2. Now we've reached the end of the input, so we ask ourselves, is the state that we are currently in a final state or a non-final state? If it is a final state, then we say, yes, this string is a sentence in the language that this DFA accepts. If it is not a final state, then we say, no, this string is not a sentence in the language that this DFA accepts. So that's the concept of an acceptor. For this string, do we accept or reject? We reject. We ended in Q2, which is not final. What's a string that is in this language? 1. If we start in Q0 and we read a 1, we will end in Q1, which is a final state.
So
Yeah.
it's not that it reaches Q1, it's the final state, it's that it
Ends
it's at the
there.
last character.
Yes.
And it's in
It
it.
doesn't matter where we've been. We don't care about storing a history. In fact, I don't know if I should spoil this at this point, but this class of automata has no memory or storage whatsoever. We saw that we didn't need that storage. I think I said that as much, but yeah, you can think of that storage kind of like RAM. The idea is this is the class of languages that can be accepted with no memory, no storage. The next question I have for you, and take a couple minutes to try to figure this out, what language is accepted by this DFA?
Binary.
It's definitely something in binary, but you can come up with some kind of number in here, like 1, 1, that's not accepted. 1, 1 is a legal binary number, but it is not part of this language. What is this language? It's some subset of binary, but how could we define that subset of binary? Think about that for a bit, talk to your neighbors, see if you can come up with some definition for this language, some way of stating the kinds of strings that this accepts. But I can evacuate for sure.
Okay, I mean, the group that I have is gonna be one.
Okay, yeah, I'll certainly be out there. Okay, will that work for you?
Yeah, I'll be fine. Yeah.
Sorry about that.
I don't know what you're thinking. Is it like prime numbers or something, and you can binary form?
Yeah, this is actually really challenging because, so the first thought you might have is that this is an odd number of ones. You see that when you get a 1 here, you accept, when you see the eventh 1, you leave, and then we see the odd one again, you get back. However, if you see a 0 followed by a 1, then you are back. So it's not quite that simple. Yeah, it's tough. We will actually come up with, I don't expect people to have an answer to this because it's not an extremely simple answer. But we will come up with the language to be able to describe this language in a bit when we talk about regular expressions. I just want to get people thinking about it, stoke your brains to think about, is there a pattern to this? There is. So we're going to come back to that. Given that we have some particular deterministic finite automaton, that DFA accepts one language and only one language, not more than one language. Intuitively, anyone have a sense of why that is? Why doesn't it accept 2 different languages or 8 languages or a DFA for an infinite number of languages? Yeah.
Have one next step state. So
Yeah. Yeah, so we always, given a particular input string, there's a single path through it, which ends in a single acceptance or rejection. So even though there are an infinite number of strings in this particular language, that doesn't really matter. For all of those strings, it will either accept or reject. And not both, and not neither. Because of this, you can classify that as a particular language. You can state its form. How about kind of an opposite question? Can there be 2 different DFAs that accept the same language?
Maybe yes, like maybe you could like reverse the direction or something like that.
Yeah, the answer is yes. In fact, for any particular DFA, there are an infinite number of possible DFAs that are equivalent to it.
Is there a proof for that?
There is a proof for that, but not one that I'm ready to draw up on the board. But yeah, you can actually come up with, there is a minimal DFA with a minimum number of states. And there may be a few of those, but you can show that you can't make a DFA that is simpler than a particular DFA. We will go through that proof. But yeah, there are so many different DFAs that you can draw. And that's one of the issues that makes this class so difficult to grade is I'm not going to prescribe that you construct a DFA in a very particular way. You're going to go solve problems, come up with a DFA to map to a particular language. And now it's the grader's task to see 20 different solutions to this and figure out for this one problem, are they right? Are they wrong? Is there a counterexample to this? How do I provide feedback on your DFA? It's a very involved process. Let's go through some examples. How about a DFA that recognizes anything with the prefix AB over the alphabet that contains just A's and B's? So now we're looking for strings with the prefix AB. Go ahead and draw out a DFA for this. So prefix AB, I'm going to go back to that, just so you can see what a DFA looks like, everything from it. You're going to need an initial state, so you need this arrow. For every state, you must draw an outgoing transition for an A and an outgoing transition for a B. They must be there for every state. It must be defined what every state transitions to on each character.
What is the statement of that? It's not going to be the word so far constructed. Like,
Yeah, so I would just start with Q0, Q1, Q2. You can name them whenever you want, really. I actually like to give them names sometimes. If it's a simple enough DFA, then I'll just do Q1, Q2, etc. But sometimes, just like variables, they could actually use a nice descriptive name. Feel free to do that if it helps you come up with the meaning behind your structure.
So if that's the case, and if something has like two outputs, like if it's A or B, but it's still go to the same state or would it go to?
Could easily go to different states. You could have one go to itself, to something could go to Q1, something could go to Q2. You have total creative control, logical control of this, aside from the constraints that I've talked about so far. Every state needs to have an outgoing arrow for every possible character in the alphabet. But a state could have multiple arrows coming into it, more than 2 arrows coming into it. Feel free to talk to your neighbors, come up with it. We'll give you a couple minutes, see if you can come up with something.
Can you go back to the problem?
Yes. Once you have your best guess, take a look at these examples and make sure that your check marks end in a final state and these X's do not end in a final state. How annoying, we are out of time. I get so engaged. I want this to be like a 5-hour class. That would probably be torture for all of you, but it's so exciting. Probably the only one who feels that way, but feel free to work on this between today and tomorrow, and we will come back and talk about this at the start of class tomorrow.
It's sort of like the non-terminal variables.
We will actually, yeah, we'll be converting between these different types and figuring out how to convert between grammars and automata as well. Yeah, they are all related.